Okay, are you ready for some more carbonyl fun? This is a great mini lecture because it's all about nitrogen, and it follows seamlessly from oxygen, its close periodic table cousin. A little review of nitrogen versus oxygen coming up. All right, little review of where we're at and where we're going. In Chapter 18, we have seen the very beginning of the introduction of soft nucleophiles. Last mini lecture was all about oxygen. Maybe a little bit of nitrile and addition of the CN minus nucleophile, another soft nucleophile, sulfur, etc. The importance of acid and base catalysis. And now we're going to apply those same principles to nitrogen. There's a weird reaction, it seems like, that's thrown into this mini lecture, but there is a reason for its presence. So let's get started. We don't get to the really fun biochemistry stuff until the end of the chapter, but let me tell you, this is definitely the realm of biochemistry. This kind of chemistry is happening in our bodies, in our brains, all over the place, all the time. So let's get to it. Like I said, this is a quick review of those crazy hard nucleophiles we've already seen. Chapter 17 introduced us to hydride reducing agents and organometallics. We've covered the oxygen nucleophiles and learned that they add 2 times to give us our hemiacetals and acetals, our stable final product being the acetal. So just to point this out, these are neither oxidations nor reductions. We have a carbon in the oxidation state of +2 in the carbonyl stage, +2 in the hemiacetal, +2 in the acetal. So, expect to see the same, right, with the addition of nitrogen. Well, not so much. Now we'll add a nitrogen, and while it's neither a reduction nor an oxidation, as we can see, it's still in the exact same oxidation state. Oddly, we don't have 2 single carbon-nitrogen bonds. We have a nitrogen-carbon double bond. So what's the fuss all about that anyway? This is called an imine or a shift base, and they are really important in biochem. So what's going on here? Why do nitrogen and oxygen give us 2 different products? Well, just hold on a second. This is such great review. Which is the stronger base? That the amine or that the alcohol? What's the difference between nitrogen and oxygen? Electronegativity. Electronegativity has an awful lot to do with the difference in this chemistry. But I will also note that there's another difference here. Nitrogen has the possibility of having 2 hydrogens on it, whereas, because of valence, oxygen can only have 1. So keep that in mind as we forge onward here. Okay, well, in the presence of an acid catalyst, we will protonate our carbonyl, and as we would expect, our great nucleophile, either the amine or the alcohol, will react to give us the all-important tetrahedral intermediate. So far so good. Nothing new under the sun. All right, what does this tetrahedral intermediate do? Well, one thing this tetrahedral intermediate does is go right back to where it started from. So I want to again emphasize that this is absolutely equilibrium. That just as protonation of the carbonyl to begin with is an equilibrium reaction, so is addition of our nucleophile. But once that tetrahedral intermediate is formed, well, we know what can happen next. We can certainly see proton transfer happen again. What base is present? Well, certainly your nucleophile, your initial nucleophile, is a good base. So deprotonation of the tetrahedral intermediate by your alcohol or your amine gets you to this tetrahedral intermediate, an uncharged tetrahedral intermediate. We know from chapter 17, no, from the beginning of chapter 18, that the oxygen version is called a hemiacetal, Well, nitrogen has its own name too, and it's a hemiaminal. So if you know anybody who got animal and aminal mixed up when they were little kids like I did, you're destined to be a chemist because there really is such a thing as an aminal. So we have two very similar neutral tetrahedral intermediates. So far so good. Still no difference. So here are our neutral tetrahedral intermediates redrawn on this slide. What's going to happen next? Well, you know, just acid-base happening all over the place, right? We could protonate here again, but that would just be the reverse reaction of what we saw on the previous slide. So, how about we create a good leaving group? I like that idea. Alright, so we protonate the hydroxyl group to make a fantastic leaving group, water. There it is, there it is. Everything looks good. And what do you think is going to happen next? Well, once you've made that good leaving group, it's going to leave. And it does. And in fact, what we can do is show that it's going to get pushed out. That's going to get us directly to these two aversions. Everything so far absolutely the same. So what's up? Well, what you should see and recognize by this point is that now we have something that can happen on the nitrogen that cannot happen on the oxygen. In one case, and only one case, can we do a proton transfer to get to a stable product. So in fact, that's exactly what happens. And as we know in our hemiacetal or our oxygen nucleophiles, this just goes back to this and gets deprotonated. Or actually, that one gets that equilibrium sets up, but this goes further to go onto your acetal. Whereas now, as we can see in the box here, we have a pretty darn happy looking, pretty darn stable imine product, all because the nitrogen can be deprotonated. So that's the difference. It's partly valence in that nitrogen has that hydrogen that can be removed. But if we look at it in a little bit more detail and think about it, it's the primary amines that allow us to get imines, because as we go back, we'll see that we actually did do two deprotonations in this mechanism. One right here. Keep going. And keep going. Keep going. One right here. Alright, so because we could deprotonate our nitrogen twice, whereas we can only deprotonate our oxygen once, there's a main reason for the difference. But in addition, there's this whole electronegativity thing. Nitrogen is less electronegative than oxygen. That means it's more nucleophilic. It's more ready to give up that lone pair, push things around. So unlike oxygen, nitrogen is more likely to absolutely push out that H2O water group, the leaving group of water. Furthermore, once that happens, imines, because nitrogen is less electronegative, they're just less electrophilic. So that pushed out water is really less likely to go back and attack the CN double bond. So that's the whole story about imines versus acetals. What about hydrolysis? Well, hydrolysis of imines versus acetals, that's identical. Basically, all you have to do is take advantage of good old Le Chatelier and add lots and lots of water to push the reaction back to the carbonyl. Okay, great. we've got imines down. Addition of an primary amine to some kind of carbonyl, aldehyde, ketone, whatever, is going to ultimately end up being an imine. Oh, goodness gracious. There it is. And the mechanism is what we just went through. But the reason that works is because I said we have 2 hydrogens on our nitrogen. What about secondary amines? Well, here's a good example of a secondary amine. And the mechanism is pretty much step by step exactly what we saw in the previous few slides. Starting with protonation of our carbonyl. Secondly, addition of our nucleophilic nitrogen. But what you can see is we end up with yet again a different kind of product. Not 2 nitrogen-carbon single bonds, not 1 carbon-nitrogen double bond, but this funky thing. And this funky thing is an amine, as evidenced by this bit, but it's also an alkene, as evidenced by that bit. So we call these enamines. So a secondary amine will add to a carbonyl to give an enamine. How and why? Well, if you run through the mechanism, which I strongly encourage you to do, you will get to this intermediate. We get to this intermediate because we had this. Let's see, make this not too ugly. We'll do it over here. There's our leaving group, and here are our 2 ethyl groups. So we get to this point, and what happens? We push out our leaving group to get, this is actually called an iminium ion. So there's my iminium ion, and of course this is reversible. What can happen here? Well, obviously, there's no hydrogen on my nitrogen that I can deprotonate to make a nice stable imine. Well, how can that darn nitrogen get its electrons back so that it's not positively charged? If you think about it, it could draw this resonance contributor that puts the positive charge on carbon. And if I do that, maybe it will become evident how I get my enamine. Because I definitely have a base present. There's my base. And in a simple E1 elementary step, I get my enamine. So, primary amines give imines. Secondary amines give enamines. And Carty assigns quite a few very handy-dandy homework problems that I have also assigned that show that enamines are a lot, are a lot like enolates. What? How can that be? Well, pretty easy, because if you think of enolates looking like that, enamines are just the neutral nitrogen version of an enolate. So, you'll see that enamines are good at making that carbon nucleophilic by simply pushing that lone pair in and pushing that guy out to react with an electrophile. Alright, more on that later. Alright, what about hydrolysis again? Well, hydrolysis revisited, this is just an example of helping you think about mechanistic plausibility. In other words, how not to lose points on a quiz or an exam. So hydrolysis means, how do I get from my imine back to my ketone or aldehyde? That's what we're striving to do. Well, we know we need to add lots of water and acid. And of course, as soon as we add acid, the first thing we're going to do is protonate our imine to get this charged intermediate. Once I have that charged intermediate, it's very likely that my nucleophile is going to be eager to react at the imine carbon to give me this tetrahedral intermediate. Now, just to keep kind of re-emphasizing the questions that you may have, why doesn't the water go here? Water absolutely does go there. That's the step. It's all equilibrium. It's all Le Chatelier. All right, so moving right along, we add our water to the iminium carbon. We get this charged intermediate. What's going to happen next? Well, certainly we're going to deprotonate, most likely, our very strong proton donor, a strong acid. So let's do that. Take our water, and now we have this neutral intermediate, and then what next? Well, why not just get rid of that darn thing? We're trying to get back to the CO double bond anyway. That should be pretty easy to do. And that would be wrong. It is not pretty easy to do, because look at this. This is not mechanistically plausible because I've got an incredibly strong acid, pKa -9 or so, -7. It's probably more like -7. And a base that's extremely strong. So this is not mechanistically feasible. The equilibrium does not favor this happening at all. So how do we get this hydrolysis to go? Well, we have to do proton transfer, yes indeed. We'll transfer this proton from here, but we will also protonate our nitrogen so that it is a good leaving group, not a lousy leaving group. And then we will kick out a much better leaving group, making this a much more mechanistically plausible mechanism. All right, one more hydrolysis, and that is the hydrolysis of nitriles. That is basically on your own, but keep in mind that nitriles are really a great friend when it comes to synthesis. You're looking at a starting material and a target that has one more carbon. Hey, CN- is a great nucleophile to add. SN1, SN2, cyanohydrin formation, they're all good. So CN is easily hydrolyzed into the amide, which is easily hydrolyzed into a carboxylic acid. It's not an oxidation, it's not a reduction, it's just acid and water converting nitrile to amide to acid. So when you see a synthetic problem like this, where I have a nice delta positive electrophile right here, and looks like I've added one carbon. Well, I can do that pretty easy by adding the nitrile in an SN2 reaction, and then hydrolysis, I've got my acid. Question for you is, there's another two-step mechanism, or two-step synthesis that you come up with to go from cyclopentyl chloride to this cyclopentyl carboxylic acid. Wonder what it is. Okay, so I think I'm going to stop here. This is a long enough mini lecture. We're going to look at the Wolff-Kishner in a separate mini lecture, and that will be very mini. But for now, just focus in on your nitrogen versus oxygen and think mechanism, and you will be A-OK.